Homework 2 is due today. On homework 1, I have one major comment that you were expected, being the engineers that you are, to look at the plot and notice that it's not symmetric. Most of you did notice that it's not symmetric because the maximum deflection at one end was different than the maximum deflection at the other end, positive versus negative. But it was much more important to think in terms of the fact that at the center of the plate, if you have a perfectly isotropic plate and you try to twist it by symmetry or anti-symmetry, whatever you want to call it, that line will have to be straight. And in fact, if you did the plot for different values of x as a function of y, you would see that it's a quadratic distribution. And that's where I wanted people to comment and say this makes no sense. Or 4 out of 55 or 56 were actually able to tell me it's because of the D16 and D26 terms. And if you, yeah, I know, you guys got it, yes. 2 of the 4. And even, in fact, plot it with and without and show that indeed it's perfectly straight if the D16 and D26 are not there, and it's perfectly flat. So the people who actually did notice that got a bonus, obviously. But the others who did not get any points deducted because it was the little extra that I was looking for. So we'll see how you guys do on homework 2, 3, 4, and so on. This is we are moving into today's lecture, and I want to start with an example. In fact, 2 examples. This example was meant to be covered last time, but I forgot, didn't have enough time, even though we finished slightly early last time. So this goes back a little bit 1 lecture ago when we were talking about post-buckling. And we are going to see what's the effect, or get a feel for what's the effect of the stacking sequence in a panel that post-buckles. Because as you will see, and that's the main message here, something that's good in buckling does not mean it's good in post-buckling, or big differences up to buckling load, let's say at buckling load, do not necessarily translate to either equally big or proportionately big differences in the post-buckling regime. We have a square panel here with the dimensions of 200 millimeters by 200. It's clamped on this end, which means nothing moves in any direction. It's immovable on these top and bottom. This immovable means basically that there is no displacement in the perpendicular direction for these edges. And all around, the W displacement out of plane is 0, and we exert a load here of a little over 2 kilonewton. The material we use is plain weave fabric, so this kind of terminology or notation should be familiar to you at this point. And we have exactly the same thickness for 2 different layups. One has 2 45s and 3 090s or 3 zeros in the middle. The other one has the exact same plies, but now they're stacked differently. The zeros are on the outside, 1 in the middle. So in both cases, these are symmetric. They have the same thickness, the same types of plies, only the stacking sequence changes. So we are supposed to determine the highest NX value when this load is applied and its location, and then see which of the layups on the basis of this is the best layup. So just all the properties that might be of interest, the A matrix for each of the 2 layups, layup A, layup B. Notice the A matrix is identical because reshuffling a symmetric laminate does not change your A matrix. But it does change significantly your D matrix, which you can see by comparing the 2 columns here for D11 and so on. Thickness is the same. In-plane stiffness properties are given here, and they would be exactly the same, E1, E2 direction, and the shear E6 for these 2 laminates. If again the stacking sequence is reshuffled and we are only calculating membrane properties which are dependent on the A matrix, in fact the inverse of the A matrix, the little A matrix, which does not change, Therefore, we would expect these to not change. Now, if I had the bending stiffness properties, then I would see a difference as I change the stacking sequence. So these are the basic properties. And we have shown that if you use a single term for the post-buckling solution, the coefficient of that single term, which coincides with the maximum deflection at the center of the plate, W11 is given by this mess here. And it's a function of the A matrix, a function of the D matrix, our applied load, and again a quantity here, which we said is the buckling load for a square plate. Units of force. Be careful, because everything we did about buckling so far was force per unit width, Nx or Nxy for shear and so on. Now, this quantity appears here in units of force, mainly because our applied load, Px, is units of force also. So the reason I wrote in the previous slide all the A matrix and D matrix properties was because I need them to calculate these quantities that go into this. And the buckling load given by this expression, when I calculate for laminate A, I get it to be 718 newtons, and for laminate B, 536 newtons. So there is a significant difference of 25% here. So it will be interesting to see how much of this 25% transfers over, or even does the trend change. But at this point, laminate A is significantly better if you want a high buckling load. Any questions so far? Okay. So the applied load of 2,000 or so is about 3 times the buckling loads we calculated. So we are way into the post-buckling. So we can calculate the W11, the coefficient in the W solution, or if you will, the center displacement, 1.67 versus 1.78. So all of a sudden, this significant difference in buckling load of 25% became only a 6.5% difference in the out-of-plane deflection. So layup A, which had an advantage because of the higher buckling load, has very little advantage, if any, when we compare to the maximum deflections in the post-buckling. Now you might say, okay, is that good or bad? Yes?
Are they now both in the same mode, let's say?
Yes. In fact, because we assumed the solution to be in the form of W is W11 sine pi x over A sine pi y over A, by construction we have assumed a single half wave. Now it turns out that for most aspect ratios up to 1.5, this is correct. It will be a single half wave. If I, however, instead of A equals A or A equals B a square, I had something that was significantly long, then this would not be sufficient. We would need more terms. If you remember when I was showing comparison from the results from that master's thesis a student was doing comparing to finite elements, when he did aspect ratios of 2 and 4 and so on, he had to not only change this value, but add many more terms. And then he found 2 and 3 half waves and so on. So the question is, big deal, is the out-of-plane displacement what you care or not? Now, in some application, if I have an entire wing, obviously how much the wing deflects can be significant. But indirectly, large deflections are associated with large bending moments at the root of a cantilever beam, or depending on your structure, you have large deflections locally. That means you may be having also large strains. So indirectly, not just because a large deflection is something we typically avoid, but indirectly this may be related to actual forces and stresses, and therefore this is an indication that a lot of the advantage from panel A has now disappeared. Now, we had the equations when we solved the von Karman equations for the coefficients K02 and K20. So just using those expressions which involve the A matrix and this W11, we can calculate these, and they both K02 and K20 are equal with each other and slightly different or significantly different between the two layups, if you look at these values. Now, since I'm trying to calculate Nx, the compressive force at any location, x, y location in the plate, I need to remember my stress function F, which was this expression from way back when 1 or 2 lectures ago. And the fact that the Nx then is given as the second derivative of this F with respect to y, which means my Nx will have this form. So just by looking at this, I can determine when Nx is maximized, which is at the edges of the panel, or I can just plot Nx as a function of y. So the vertical axis here is Nx, y over a, it's normalized, so it goes from 0 to 1. And this will be the exact same plot for any location of x location along the plate. Yes, if you are exactly near the edges, the boundary conditions have an effect. The Saint-Venant's principle kicks in or doesn't kick in, but as long as you are a little further away, this is a very good approximation of what happens. And as you see now, the two layups have at most a 3.7% difference. So all this improvement in buckling load from one laminate to the other has translated to a tiny 3.7% increase in Nx, which would be 3.7% increase in your stresses and so on. So the message here is don't assume that buckling load is an indication of good post-buckling performance. And in fact, you need to decide what is it that you want in post-buckling. Someone might argue, I want a very compliant structure that can deflect a lot as long as this is relatively uniform large deflection everywhere. Or someone would say, I don't want large deflection. So don't make a decision about a stacking sequence until you have run the numbers and decided that, okay, for my application in the post-buckling, if I want to postpone failure in this way, I will need the lowest possible stresses. And then you find which laminate gives you that, irrespective, or taking into account also what the buckling load is. So buckling alone is not even half of the story. And if we're going to do a failure analysis, let's say first apply failure, there's a 3.7% increase in Nx, which for all practical purposes is even within experimental scatter for most types of tests. So I could argue that the two laminates are about the same when it comes to post-buckling performance. One minor note is everything was about Nx here, and there will be an Ny and Nxy, and the three moments will be present in the plate. Nx is the most critical, that's why we confine the discussion to that. That does not mean that you shouldn't check all the other Mx, My, Mxy and see if indeed maybe one of the two laminates is significantly worse because one of those quantities is much higher, and therefore you would have a failure in a different mode than the one we're considering here, which is under pure compression. In general, as a very good start in these problems, Nx is sufficient, but then once you start finalizing your design, you should look into the other quantities also. Now, the only reason that our designs might have a difference is about when it comes to damage tolerance. Remember my stacking sequence, or our stacking sequence. Well, let's look at this. In one case, I have 0.90s on the outside. In the other, I have plus or minus 45s. So, and I have a 3 0.90s in the middle here, while here they alternate. Now, there are reasons why one would be better than the other when it comes to impact, resistance to impact, and then what's the compression after impact strength. We'll talk about those in the next course because it's lectures and lectures worth of discussions on that. Going back to crippling that we more or less finished last time, this is an example now in crippling, and in particular a stiffener which is actually under a bending moment rather than the pure compression, just to see the effect of local tension versus compression parts of the structure. It's an L or angle stiffener, B1 and B2. The B1 is kept fixed to 17.78 millimeters. You know, nothing like picking numbers out of a hat and being correct to the second decimal. But this again come from English units, so in English units it's a much nicer round number. And the bending moment is 22.6 Newton meters. And we are also told that our room temperature ambient compressive mean undamaged strain, ultimate strain is 12,000 microstrain. That would be 0.12. 0.012. And we want to find the maximum value of B2. So as I change my B2, I will be improving my bending stiffness, because the I about the horizontal axis, wherever that neutral axis is, will be increasing tremendously, which means the bending stresses are going down. But at the same time, as I increase the B, my B over T increases. And if you remember from our plots for crippling versus B over T, we start with a nearly horizontal line, and then it goes down, this being the crippling stress divided by the ultimate compressive stress. So this reduction means as I increase B, this is going down, which is not good. At the same time, as I increase B, my moment of inertia is going up, which is really good. The question is, when do those two meet each other to get the best possible solution? Because if I'm one way, then I'm failing because of the stress being too high. If I'm on the other way, I'm failing because the crippling resistance is too low. I think I said the same thing, but one way, the crippling stress is too high. The other way, the applied stress, bending stress is too high. Now, disregard the second question. We will do it in the long run as part of the end of this lecture and the next lecture. So, for the stacking sequence shown in the previous slide, where is my stacking sequence? Skin layup. Oh, don't worry about the skin layup. Okay, here it is. 45 minus 45, 0 to 90 symmetric with an overbar, which means 90 does not repeat about the mid-plane. So the A matrix and D matrix are given here. Notice Webb and stiffener have the same stacking sequence. This is not the most efficient, but just for the purposes of the example. And the corresponding membrane Young's modulus and bending Young's modulus are shown here. Thickness 1.37 millimeters, and my zero fibers are aligned with this direction 1 here. So first I need to calculate my neutral axis, and because the two members have the same E, or the same layup, they have the same E, which means when I calculate my neutral axis, each term would have an E there because it's summation of the EA divided by the summation of the areas. But these E's being the same would cancel out, so I'm skipping an extra step. And that's not correct, is it? That's better. Well, I'm missing a times Y. EA of I, YI, summation of EA, I. So at the numerator is the EA of the member of which that will contribute. That's not right either. Well, there's summation here. What's my neutral axis equation? I have to go back to first year. I bar is sum on both sides, but this should be in, no. How do I get rid of? Yeah, this is correct. Finally. Okay, obviously I do not know the basics. Each member times its distance from the reference axis divided by the sum of all the EAs. And if all the members have exactly the same stiffness, what I was trying to say was that the E's will cancel, so I can resort back to my standard equation for Y bar. The reference axis about which I calculate the Y's are shown here. And this is a function of B2, which in our problem is a parameter. We have to vary B2 and find what's going on. And the corresponding moment of inertia, once I know my Y bar, is my standard contribution, the BH cubed term over divided by 12 from the vertical part, and the Steiner term from the horizontal part, plus the Steiner term from the vertical part, plus a moment of inertia about its own axis for the horizontal flange. The main point is that B2 appears here as a variable. Now, if I know my neutral axis, then I know that under a bending moment I will have a compression part and a tension part, and I need to calculate my maximum compressive stress, which is given by the bending moment times the distance from the neutral axis divided by I. If I know the stress, bending stress, I can calculate the corresponding strain. This being a beam, I can directly divide by the Young's modulus, which is this one. So this gives me my strain. So this is my applied strain for a given bending moment and a given selection of B2, which means that as I change B2, this would change. From a crippling perspective, we said find the part that's under compression, which is this portion, and that's the B that goes into the equation that involves the crippling stress calculation. And when we do that, if the distribution is linear, then take the average maximum to minimum. So that would give us the maximum compressive strain divided by 2. Notice I'm using strains here because they are directly proportional to stresses through the Young's modulus, so it doesn't matter if I do it in terms of stress or in terms of strain. The reason I'm doing it in terms of strain is because it was given to us that the structure has a 12,000 microstrain maximum strain capability, and I'm going to use this for and reference everything to strains. The crippling stress equation for one edge free, which is the top of the vertical web, is given by this quantity. And if I translate this to strains, epsilon crippling divided by epsilon ultimate, it's the same as multiplying with ease. So this is the strain at which, given a value of B2, we would have crippling. And this is the strain that at which we would have material failure. So we are essentially comparing two things, or two failure modes, material failure and crippling. And I have been using the knockdowns corresponding to environment, damage, and material scatter, the standard knockdowns we introduced at the beginning of this course, just to translate it into a design value of 5,000 or so microstrain. So if I take that strain, which is now my ultimate strain, I put it in my crippling equation, and that gives me the crippling strain as a function of B2. Remember, Y bar is also a function of B2, so this quantity here, even raised at the 0.717 at the denominator, is quite a mess. It's not something you can solve analytically, you'd have to do it numerically. And as I said earlier, the compressive applied strain as a function of our bending moment is given by this quantity, both of which are a function of B2. So in principle, I could plot these two and see how they vary as I change my B2, the web height. And what I notice is obviously both are decreasing, but the applied strain is decreasing much faster. Basically, the effect of the moment of inertia increase by increasing B2 is much larger, and therefore by increasing the moment of inertia proportionately much more than you are decreasing the B over T, you are getting a maximum applied strain going down faster than the crippling strain, and they would meet at a point. And that is our answer. At this point, we have both things happening at the same time. On one side of it, for larger values, we would have the blue line coming below, which would mean that we are failing because of the bending strains exceeding the strain capability. On the left side of this, we are failing in crippling. So smack in the point where the two intersect, we get the optimum answer, which is what the problem was about. Any questions? Okay, now let me switch to today's discussion. Which is more about stiffened panels and crippling again. We will have an example where we will discuss the load between crippling and the load between stiffeners and skin and the different failure modes. One more failure mode for the stiffeners alone, inter-rivet buckling. Then we will juxtapose or compare inter-rivet buckling with crippling, and there will be some important implications about fastener spacing. And finally, we will start about stiffened panels, which will take the best part of today and next lecture, and I think the lecture after that, where we will bring in together stiffeners and skins and see what we can make out of all this. So let's do first the example. We have a stiffened panel with a J stiffener that we've been on and off designing throughout the course. We have arrived at this configuration at this point. Doesn't mean it's the best possible configuration, but with this one, we make 4 stiffeners, shown here in light blue, or whatever you want to call that color, on a stiffened panel, and we are concentrating on basically the dimension between stiffeners. If you will, I can eliminate the outboard section of the skin. It won't change my answers. It's important when it comes to attaching, but that's not part of the discussion for this example. The skin properties, D matrix, this means should be times 100, so these values are 100 times smaller than what they should be. But anyway, these are the properties for the skin. The skin thickness is 0.57. The A matrix is here, and for the stiffener, the dimensions are what we had arrived last time. We revisited this stiffener design in terms of the B's and the T's. B's are the length or width of each member, and T is the thickness. And for this stacking sequence that we have so far selected, not necessarily being the best possible, the corresponding membrane and bending stiffnesses are shown as the last 2 columns. What we are supposed to check is when the load is 100 kilonewton, what's happening to the structure? Is it failing or is it not? And in what mode is it failing? And what is the critical part in the structure? Now, anybody knows what the critical part would be in the structure? I mean, whether you've seen the lecture or not doesn't matter. Is it the skin or is it the stiffeners? How many think it's the stiffeners? 1, 2, 3, 4, 5, 6, 7, 8. Okay, how many think it's the skin? 1, 2, 3, 4, 5, 6. Or 7 still. The guys who said skin are correct, so it is going to be the skin. Of course, it's easy for me. I know the answer. I wouldn't have been able directly just by looking at it saying what happens and why. And it's kind of interesting because it relates to the B effective, the effective width of the skin that we said is going to contribute to the stiffener performance. And we're about to see that. First, we will require, based on our discussion, that the skin buckles in between the stiffeners. Somehow, hopefully, the stiffener we just saw has the right bending stiffness to keep the skin from buckling locally, and therefore the stiffeners will stay straight, the skin buckles in between. The exact requirement for this to happen, to force the skin to buckle in between stiffeners, we'll cover in the next lecture. But for now, let's say this is correct. That means I can treat my skin between stiffeners as a simply supported plate, which is one of the most conservative things we can do. And we know the buckling load then is given by this quantity. The D is the D matrix for the skin. The M is the number of half waves. The aspect ratio is the length divided by width of the portion between the stiffeners. It's not the aspect ratio of the entire plate, but it's the length divided by the width for each of these little bays created by the presence of the stiffeners. So the calculation says that the lowest buckling load occurs with 3 half waves along the length, M equals 3. This is the buckling load in newtons per millimeter. And that means now that my post-buckling ratio, which is the ratio of the total applied load, divided by 457, which is the width. So this is 100 kilonewtons, divided by this makes the load in load force per unit width. And if I divide that by 182, which is this buckling load, I get 1.2. That means that the skin buckles, and in order to reach the full 100,000 newtons, I would need to keep increasing the loads by another 20%. There is a question here, what does that mean about your skin? Now, presumably, after buckling, we have covered post-buckling, so one way would be to do the post-buckling analysis the way we said. The conservative way is to assume that the skin will not be able to carry any load beyond buckling. So any load increase beyond this would translate to an increase in load in the stiffeners. Now, this is valid as long as the stiffeners are stiffeners. The word stiff means they are stiff compared to the skin, and therefore they can absorb most of the load compared to the load that goes into the skin. It's not guaranteed it will happen. You have to make sure your stiffeners are stiff enough so that this occurs, but that's a matter of playing with the EAs again. You can take the EA of the stiffener, the EA of the stiffeners, divided by the EA of the skin. And as long as the EA of the stiffeners is 10 times or something like that bigger than the EA of the skin, then it's a safe bet that most of the load, 10-to-1 ratio is the ratio the load goes into the stiffener versus the skin, would be a safe bet. So this assumption is a good assumption, especially for a quick calculation that we're trying to do here. Now, what is the load in each stiffener? What's the load in the stiffener and what's the load in the skin? Now, this load in the stiffener is the total load minus the load in the skin. We said the buckling is at 182 times 457, which is the total width of the skin to make the newtons per millimeter into newtons. That's the total load left to be divided among the 4 stiffeners. We have 4 stiffeners. Divide by 4, that's the total load in each stiffener. Now, the skin only, obviously, is the 182 buckling load times 457 divided by 4. Why do I divide by 4? I want to isolate each part of skin next to each stiffener just as a matter of convenience. So basically, I take a portion of the skin that is associated with this stiffener, a portion with that one, and so on. It's just a matter of convenience. That's why I have that division by 4. So each portion of skin that's near a stiffener, equally distributed, carries this kind of load. Now you can start seeing that potentially the skin will fail first because the load in the skin, due to a not so good selection of the skin stacking sequence, is 5 times the load in each stiffener. Okay, so let's look now at this configuration. There's this stiffener, which is the stiffener we've been using all along throughout the course. And then there's a portion of the skin that is associated with that stiffener. And how much of that skin do we take? Remember when we talked about the effective width, we said it has something to do with its importance comes in also during the post-buckling. And because the load in a post-buckle panel is all concentrating at the edges of the panel, and in fact, B effective is a representation of the region of high intensity of load, then we can assume B effective on one side of a stiffener and B effective of the other, on the other side being the portion that contributes to the load carrying ability of the local structural detail that we call now the stiffener in the skin. Now, the effective B from the equations we derived during post-buckling as a function of A, that A was the width of the panel, and when we evaluate this expression, you get it to be about 0.3 of A, and given now the width between stiffeners or the spacing, you can find that this effective B is 4.45 centimeters. Notice in blue at the bottom it says that we are assuming the panels, the skin between the stiffeners was simply supported to do our buckling calculation. But for our post-buckling calculation that we used to determine B effective, it was a slightly different boundary condition. It was still simply supported in terms of out-of-plane displacement, but it also was constrained in the in-plane direction. So there is a bit of an inconsistency here, but the main message will still be the same. If you refine it, you get about the same answers. The skin stiffness is 1 divided by little a11 for the skin and the skin thickness. So when you do that, you find 41 gigapascals. So the structure, or each portion of the repeating unit or repeating structure, is divided into 6 members. 1 is the horizontal flange at the top, 2 is the vertical web, 3 and 4 are the 2 horizontal flanges, and below those we have the B effective to the left and B effective to the right, which are 5 and 6, are again parts of our configuration. So here, not only do we use the stiffener, but also the skin portion has 6 members. Each has a certain width B, the values here, the thickness, value shown here, the corresponding Young's modulus, the corresponding area, and then the corresponding EA shown here. Knowing the EA, I can calculate how much of the total force is on the ith member. Basically, remember our equation that Fi is the EA of member I divided by the summation of the EAs times the total force. That's what we had said before. In fact, hopefully I can readily produce that chart here. No, here. The force in member I is just the EA divided by sum of the EAs. So the last column, therefore, is just the ratios of the EAs divided by the sum of the EAs. And it's telling us that members 3 and 4, which are the flanges at the bottom here, take 25% of the total load each, 24.9. The member 2, which was mostly 45s, is not that effective, carries less than 10%. Member 1 is quite good for its dimension because it's small. Look how small it is. It's carrying 15%. Our trouble area will be, or will turn out to be, these 13% of the load that's into the skin on the 2 sides of the skin. Because I can now calculate, given the ratios of the forces, the corresponding applied force by taking the total force on each of those skin stiffener configurations, and calculate the corresponding applied stress, because I divide the load by the corresponding area, and that will give me the stress for each of those members. And now we do our crippling calculations. And we have member 2, which is the vertical web, is no edge free. That's the only one that's connected on both ends. And everything else is no edge free. Right? What did I say? Member 2 is no edge free, and then, oh, sorry, the last 2 are also no edge free, and that is a bit of a subjective assumption. What we say is that right here, the fact that I have a vertical web with a flange connected acts as a pin. You can debate that, but that's a reasonable assumption. And we also say that because we are assuming all the load in the buckled skin stays at the B effective, the load here is 0. Basically drops to 0 outside of the B effective. So it's conceivable that I have some kind of a simple support at these points, and therefore I treat these as no edge free. If you wanted to be more conservative, you would treat them as 1 edge free, and it would be even worse in terms of the final result, but that would point to an area that you need to redesign. So the B over T for each is calculated, and notice how big the B over T is for the skin portion, 78. That's really, really large. We're moving way out here on these plots. Knowing the B over T and the equations for crippling, 1 edge free versus no edge free, we can calculate the ratio of crippling stress to the compressive ultimate strength. The compressive ultimate strength calculated as a first ply failure of the corresponding member under compression is given in the next to last column. So by multiplying these, we can calculate the allowable stress for each member. That's the stress at which we get crippling. So crippling would occur for the first one at this load, and my applied is 40. So 40 is less than that, so I'm in good shape. And so on, if I take the ratios, anytime the ratio is smaller than 1, I'm in good shape. If it's greater than 1, it means my applied stress is much larger than the capability of the structure in crippling. So this clearly says your design is miserable because the skin fails, and it fails by a lot because this is a pretty big ratio. So, yes.
The B that we are using for member 5 and 6, some part of that is underneath of the stiffener.
Mm-hmm.
So it means that I have this feeling that they are supported by the stiffener. So if they're not buckling,
well, that's why I said I could hopefully treat this point, because of the support, as a support to define this member as a having that width and it being no edge free. Basically, you are saying, okay, it's supported up to here, so somehow that should be accounted for. And I'm saying, oh, I don't know exactly how to account, other than saying, instead of treating this as a completely large member, I would split it. That divides my B in half, and it would still be reasonable because of this entire stiffener supporting the skin at that location. This is all open to debate, and I like your argument, and it would be worthwhile trying to come up with a better model to see if indeed this kind of ratio is as bad as it appears or not. One simple point is that these ratios are not only less than 1 for everything that does not fail, but significantly less than 1. So conceivably, you could take now some of the load from the skin, say, okay, I'm going to allow it to fail, and any extra load will go to these guys according to their own EAs. And if I show that it doesn't fail, I can claim that while I do have first failure at that applied load, that load can be redistributed to the stiffener, and that would be sufficient. That's one way. May not be the best, but any approach to improve this design is up to whoever wants to do it to think about it. So let's reconvene in 15 minutes. Discussion and basically do a small update. We discussed what happens in the regions of pockets that are created because some plies terminate, some turn around, and some are continuous below. And we showed last time that you can get a significant load capability up to 30%, maybe even if you make this material, the filler, to be a unidirectional tape, which typically has fairly high stiffness. So now our update says wherever we have these potential pockets or voids areas, we actually fill them with filler, and let's even say that it's going to be unidirectional tape strips. So this is our current design, and one of the questions is how stiff is this flange here? And remember, for the example we were just doing, the skin had only 3 plies of fabric, this skin here. So this is extremely soft compared to the very high or relatively high stiffness of these flanges. So we know that if this is the design that we are sticking with in terms of the skin layup, this is probably a problem area because of the high stiffness mismatch between the flange and the skin. And exactly what that means and how to analyze, we will do in a couple of lectures or so. But so far, this is our next update on our stacking sequence. And why I have this here, I'm not sure, but it's the same thing, pretty much. Okay, one more failure. Just when we thought we had column buckling and strength and crippling, now we have the inter-rivet buckling. Basically, buckling can happen at different wavelengths, the full length of your structure or a shorter wavelength, and then that shorter wavelength can be anything from the very small crippling wavelength to something intermediate, which is the fastener spacing. So if your flange is under compression and it's attached to a skin or some other structure with fasteners, then if the fastener spacing is large enough, then you can actually buckle the flange with half wavelength equal to the fastener spacing S. So why would you use fasteners? Because ideally you would want to co-cure the stiffeners on whatever bond, basically the stiffeners on whatever adjacent structure you have. It's cheaper and probably slightly lighter. As I was saying last time, however, inspection, which is required to be able to tell if the structure is performing as it should, inspection methods of today cannot detect a bond line that is not 100% of its strength. Basically, the adhesive can fill everything, so you cannot detect any voids. But if it's somehow contaminated or the chemical reactions during the setting of the adhesive was not good enough to create the adhesive bond between the adhesive and the members such as the flange and the skin, if it's not there, then you cannot tell. In fact, there's a lot of money to be made. If someone can come up with a method to do that, you become an instant millionaire. So because we are not allowed to simply have primary structure with a bond line alone, unless you show that you can remove 50% of the bond and you can still take limit load, or you are showing that if you remove 50% of the load, the adjacent structure will redistribute, the load will be transferred to the adjacent structure and there will be no failure. Unless you do that, which is typically fairly heavy solution, you have to use fasteners. So fasteners are used for this reason, to protect against failures in bonded structure. Also are used to protect against the skin stiffener separation problem. We'll talk a lot about this in the future lectures. But the point is, if the structure intends to separate, skin buckling separates, you can hold it there with fasteners. Fasteners are extremely good at doing that. So you will remember way back then we said there's an equation that keeps reappearing, which is this one. This was first or second, no, third lecture maybe. So this equation is still, when in doubt, we start with this equation. So we start with that equation again. And we say that the flange is treated as a one-dimensional structure. So there's no dependence in y, there's only dependence on x. So we take that equation and we remove all the dependence in y, which means all derivatives with respect to y are 0. And we are left basically with the d11 term for the flange, the unknown out-of-plane displacement that the flange will go into during inter-rivet buckling, the applied load nx, which becomes, I call it n0 being minus nx, so if n0 is positive, it means I'm under compression, and again the second derivative of w. And in fact, once I did this and I said there's no dependence in y, I can change the partial derivatives to total derivatives, but for the purposes of consistency, I keep them as partial derivatives. Now, during buckling, from second year structures all the way through here, we have seen the solution of this equation, which involves a constant, C0, a linear term, C1x, and then two trigonometric, a sine and a cosine. Now, the Ci are to be determined from the boundary conditions, basically these four constants. And let's say, for now, that we have simply supported boundary conditions. Up for discussion whether a single fastener here causes a simple support across the width of the flange or not. If the fastener diameter is small and therefore the collar and the nut are small, it's quite unlikely that they will enforce zero displacement across the width of this flange. But let's solve it for simple supported to see what type of a solution we get, and then we will come back to the effect of the fasteners themselves. Simply supported means that there is no displacement at the two ends, so at x equals 0 and at x equals s. Remember, s is the spacing of the fasteners in this case. And because it's simply supported, there is no bending moment, so d11 d2w dx squared with a minus sign is equal to 0. In its general form, it would have a minus d12 d2w dy squared minus d16 2d16 d2w dx dy, but because those involve derivatives with respect to y, which are neglected here because there's no dependence on y, this is our condition. So at the two ends, where the fasteners are, zero displacements and zero bending moment. So let's translate our solution w into these conditions, or substitute into these conditions to see what we get. That condition that it's zero displacement at x equals 0 gives us a C0 plus a C3 equals 0. The corresponding condition at x equals s will give us this whole mess that involves C0, C1 times s. It's evaluated at x equals s, so whenever there was an x before, there's an s now. The bending moment at x equals 0 gives us this condition, and the bending moment at x equals s equals 0 gives us this condition. So from equation number 3, that's the easiest one because n0 and d11 are non-zero. We want a solution for a non-zero N0 means C3 equals 0. As soon as C3 equals 0, I can come to this equation, and then C0 is 0. So those two are out there. I skip equation 2 for a second, and I go to equation 4, and I impose my C3 equals 0 condition. So I'm left with C2 times this quantity would have to equal 0. Either C2 is 0, and then I will find that there is no solution out of plane buckling at all, or C2 is non-zero, and that means because N0 and D11 are non-zero, I'm left with this sign of N0 D11S equals 0, with the square root of this, and that means that square root quantity must equal N times pi. So I can back solve for N0 to get the well-known solution, N squared pi squared D11 over S squared. Now this is identical to our column buckling P critical equation, which says pi squared EI over L squared, L being the length, or in this case is S. If you notice that this is in units of force, this one is units of force per width, N units of force per width. So the EI term is actually replaced there by D11 times width. So, if I divide this by width, then EI divided by the width gives me my D11 term. And you can show that because D11 typically is proportional to a stiffness times a height, EH cubed, over 12 times 1 minus nu squared. This is proportional because in reality D11 involves the summation of the QIs and so on, but this is the kind of term that's there. And now you can see that the h cubed divided by 12 times 1 minus nu squared is just the I divided by I per unit width. So there's a BH cubed term there. So in principle, we recovered what we already knew, if you will, that the buckling load is given by this pi squared over S squared times D11. N is set equal to 1 because that's the lowest buckling load. And if I divide that by thickness, I make it into stress. So this becomes my inter-rivet buckling stress, which is given by this quantity pi squared D11 TS squared. Now that's the case of a simply supported structure. And as I was saying, that may not be the really what's happening. It turns out test results suggest that if you have countersunk fasteners or rivets, then this equation here is pretty close to test results. You can adjust it based on test results and the type of countersinking and so on, but in general this is good enough. So if I put in a constant C and I set it equal to 1 for countersunk fasteners, I would get a very good prediction using this equation. If I set it equal to 3, I would get the story of the protruding head fasteners. Protruding head fasteners like these guys start approaching essentially the clamped condition. Remember, for clamped condition, this C would be 4 because the buckling load in clamped beams is 4 times that of simply supported. So we are a little bit before this, the clamped, and it's a factor of 3, which is purely experimentally determined. There is no magic about analytically finding the value is 3. You just do a bunch of tests, and you try to fit this times a multiplier to the test results, and it turns out if C equals 3, that's the number that you will get good agreement with the test results. So if the fasteners are spaced a large distance away, S is large, then I can have inter-rivet buckling. If the fasteners are very close, I don't have inter-rivet buckling. So what's left? Either the material failure or the crippling. The material failure is for B over T very small, which is this horizontal portion of the curve, and then crippling part kicks in once the line starts sloping down. And this is a straight line on a log plot, or it would be a curved line on a linear plot. I can therefore start wondering when I switch from one failure to the other. If I start from very small fastener spacing, I have crippling, and as I keep increasing the fastener spacing, then all of a sudden I will get inter-rivet buckling, and then that's the one that will dominate. So in a sense, I can anticipate this kind of curve, which says the failure stress is given by the crippling stress, and as this fastener spacing reaches a critical value, S maximum called here, then I switch to the interrivet buckling. Don't get confused the shapes of these two curves. Notice the x-axis here is B over T. The x-axis there is the fastener spacing S. So as a function of S, once you have crippling, as a function of S, it's a constant value. Even though it changes, the crippling load changes with B over T. But B over T are unrelated to S, the spacing of the fasteners. So if I equate, basically to find this point where I switch from one failure to the other, I would equate the crippling stress with the interrivet buckling stress. And if there are, and let's say I took the case of one edge free crippling, I would then back solve for the spacing S max. And I would get this crazy equation that's telling us that if the spacing is bigger than this value, we will have interrivet buckling. If the spacing is less than that value, we have one edge free crippling. Obviously, if you have flange that's no edge free, then you wouldn't be using this equation, but that's left to the interested student to derive the expression. So what does this mean in terms of, okay, what are typical values that one would get using this interrivet buckling calculation and the crippling? You'll see that it makes a big difference now what type of flange stacking sequence or layup you use. And let's take a good stacking sequence and a bad stacking sequence for a flange. Basically, the good one is the one that will have a bunch of 45s, because we said 45s are good because of the D66 term present in the crippling equation, and therefore they will delay buckling. But it needs also a bunch of zeros so that the compression ultimate strength is as high as possible. So this is a good design for a flange, and this is a bad design because it has only this half fabric ply 0 and a 90, which doesn't do anything for a flange in under compression, and then it has only these two 45s there. So ultimate strength for the two stacking sequences, you can see here the significant improvement when you have more zeros. The corresponding D11, it's a ridiculous difference. It's not even funny how bad the bending stiffness of the second laminate is. And of course the thicknesses, and as you might expect, part of the problem in the difference in D is because this 3-ply skin is, or 3-ply flange is very thin. One note to start talking about good designs, it says here this layup has too many 0-degree plies stacked together. Basically, if you think what happens at the mid plane, I have 4 plies above the mid plane and I have 4 plies below it in order to maintain that stacking sequence that we wrote. 8 0 plies next to each other is not a good idea when it comes to microcracking. When you cure and you cool down, or when you have a mismatch of thermal expansion coefficients that might locally lead to stresses that tend to put the matrix in tension, you get microcracks. Once you get those microcracks in between the fibers, if each ply is the same as its neighbor, there is nothing to stop these cracks from extending the full thickness of the plies of the same orientation. So 8 plies is a bad idea. Typically, you don't want more than 3 or 4 of the same kind. I think we'll cover that at the very last lecture more. But keep in mind, basically, that here we have a phenomenally good flange design, which, however, would have some microcracking problems, but we push that aside just so that we can continue with the example here. Let's take the 3-ply fabric flange, which was the rightmost column in the previous chart, and plot this maximum fastener spacing, S max, as a function of B over T. So what we find, okay, there are 2 curves, one for the protruding head because of the factor of 3, and the other for the countersunk fasteners. Typically, a flange to width ratio is anywhere between 5 to 30, let's say. So on this axis is approximately in this region here from 5 to 30. what we see is that whether it's countersunk or protruding head, for any of these B over T values, the corresponding maximum fastener spacing is no more than about 20 millimeters. Basically, if you had protruding head and you were out here, you would get about 20 millimeters. That means if you had more spacing, you would actually have inter-rivet buckling. And that's a problem. That's a major problem. The spacing basically that this flange requires to avoid inter-rivet buckling turns out to be less than 20 millimeters, would have to be in this vertical region lower than 20 millimeters for any typical B over T used in practice. Now, why would that be a problem? Let's talk about what happens in a structure with fasteners and load being transferred from one member to another. Now, this is not a course about joints. There's a special course that does this, but it's good to put it in perspective. Suppose I have the blue laminate and the light blue laminate, both under load P, and I have 3 fasteners. In fact, when you test it, it looks something like this. You will see that the fasteners tilt like crazy and they start digging into the structure, into the composite. The load P reaches a fastener, then some of that load splits and goes into the light blue laminate, and some of it continues on. And in fact, it turns out by symmetry, and because I have only 3 fasteners, you can find that if you call P1 the load that is transmitted right after the first fastener, then P minus P1 is the load that's left, and then that P minus P1 hits the next fastener, which will have to transmit back to a P minus P1 here and a P1 there, such that you maintain the anti-symmetry of the structure here. Now, that means that the fact that I have load on either side of a fastener means now that this load, P minus P1, let's say approaching the second fastener, will see the stress concentration effect of the second fastener. And the load P approaching the first fastener sees the stress concentration effect of the first fastener. The closer the fasteners are, the more they interact with each other. So if in an infinite plate there would be a stress concentration factor caused by one fastener, which is not 3 because the fastener has a bolt in there. It's less than 3, but it's significant. If I have a finite plate with fasteners next to each other, this stress concentration factor is increased by the presence of the other fastener next to it. In fact, a lot of tests with typical laminates have shown that if your spacing is less than 20 millimeters or so, that's for typical fasteners, typical flanges, but that's a good number. Then the interaction or the enhancement of one stress concentration factor by the presence of the next fastener is too much. It increases the local stresses by a factor that we do not, it makes it very difficult to come up with a lightweight design. So as a rule, you want to space those further away. Now remember, that doesn't mean you can space them as far as you want. First, because you have inter-rivet buckling, but second, because if you are trying to hold a flange onto a skin and you have only very few fasteners, then in between, the flange under loading will start bending and things can go in between because you create a gap and you can get moisture, you can get all kinds of contamination on top of the issues of inter-rivet buckling. So, if 20 millimeters is the rule of thumb to avoid this interaction between successive fasteners, and if this design here with this flange tells us that we need something less than 20 millimeters, then this is a very bad design. So to make a long story short, if you use soft flanges, it's not a good idea. Of course, you have to run the numbers, but this is the kind of problem you run into. If you take the other laminate that we said is a good laminate for this situation, despite the microcracking problems, then the corresponding plot looks like this. Again, the vertical axis is this maximum fastener spacing allowable to avoid inter-rivet buckling. And for any B over T ratio that we might care to use, both curves, the countersunk and the protruding, are above the 20 millimeter spacing of fasteners. So basically here, Inter-rivet buckling is not a driver, and you can use any spacing you want as long as it's less than 20 millimeters, as long as it's more than 20 millimeters, and you would be fine both from the perspective of avoiding stress concentration enhancement and from the point of avoiding inter-rivet buckling. Any questions? Okay, let's start. Yes, please. If I, okay, so one is here, you mean this versus this? Is that what you meant? So if the load is in this direction, and this is my flange, besides each other like this, so if I have them like this, yes, well, again, what you want to avoid is this distance being too close. Now, there's a rule that covers all this. I mentioned 20 millimeters before as a good minimum distance. The rule is 4 to 5 fastener diameters. Once you pick your fastener diameter, as long as in any direction around it, irrespective of the load direction, as long as in any direction the next fastener is at least 4 fasteners, preferably 5 fastener diameters away, then all the problems that we mentioned with stress concentration effects are almost completely eliminated. There is one additional requirement that we will cover hopefully later on, which says, okay, what's the distance of each fastener from the edge? So there is the edge distance problem, and there is the fastener to fastener distance problem. Fastener to fastener is 4 to 5 diameters. For composites, for metals, you can get away with smaller, 2.5 even. Edge distance is 2.5 diameters plus 1.3 millimeters. Now, why it's 1.3 millimeters, we'll cover later on when we get back to this discussion. But these rules presumably cover those concerns. In general, depending on the direction of the loading, the spacing between fasteners can be worse in one direction than in another. To avoid having to consider which way is the loading, because this is a simple case, if I had a combined loading like shear and compression, then you actually have to resolve the forces, and that makes it harder. In general, the rule is 4 to 5 diameters, and you are golden as far as this problem is concerned, and 2.5 plus 1.3 millimeters for the edge distance. Now I'm not doing this. If I could do this with my own brain power, move the whole buckling, is it? Or is it electromagnetic interference? Skin stiffened structure. So we did plates, buckling, post-buckling. We did stiffeners, crippling, inter-rivet buckling, buckling on elastic foundation or no elastic foundation. So it's time to put them together. So, and see what happens. Let's take a generalized case with generalized in-plane loads. And as a background, the skin takes compressive loads. Well, okay, I said pressure there. The skin takes pressure loads, membrane action, like a balloon. It takes shear loads, and it's interesting, compared to compression, skin also takes compression loads, but only up to skin buckling. Once it buckles, there is some post-buckling capability, and we've done analysis methods, but it's not as good as it is under shear. So if I have a skin under shear, in fact, post-buckling can do extremely well. And let's see if you can help me to figure it out. So this is my skin under shear. What happens if this buckles? It will go into these half waves, as we've said before. Let's say there are 2 half waves along the length and 1 along the width. And the question is, okay, this has buckled. What is the local load anywhere if I take my little square and I find what are the local loads to get the discussion going? As we said before, the pure shear becomes a tension in this direction and compression in that direction. So if every single square here has tension in that direction aligned more or less with the diagonal, in fact it's aligned with these half waves, and compression perpendicular to that direction, as I increase the shear load from 0 and I keep on going past the buckling load, minding my own business, what happens into these little squares? And suppose, to make, anticipating this is in a shear application, this being a shear application, I put fibers in the plus or minus direction. So the fibers are running this way, plus or minus 45 degrees. So what does the compression part do? Tries to buckle, it buckles the fibers even, let's say, okay, it completely destroys the load carrying ability in compression. But let's think about the tension part of the load. We are putting fibers in tension, and unless we pick a really bad material, that's what fibers are good for, in tension. I mean, even if you removed completely the matrix and you had all these fibers and you were pulling in tension, you would have a phenomenally good performance. This doesn't happen in a pure compression case. Pure compression, no matter what your layup is, you will not achieve a part of the structure that's completely in tension, and that tension load would be the majority of the applied load. Here, basically, you can say all the compression load is destroying or is failing the structure in compression. And as I keep increasing the load, what I'm doing is I'm keeping the compression load constant to that failure load, but the tension can keep increasing. So I can actually effectively keep increasing this, and until I break fibers in tension in the plus 45 degrees, I have a good performing structure. So shear, the skins, that's why skins take shear loads. That's why we do shear flow calculations for skins, because that's what they do. It's the best thing they can do. They take pressure loads, not terribly well if you have a crack, but the main thing is they take shear loads and they can go way beyond buckling. While when it comes to compression, they can really go up to buckling and a little bit post-buckling depending on how you do your design, and if you can design away from the failure modes in the post-buckling regime. Stiffeners take bending loads and compression loads along their length. That's pretty much well established. So let's cover the concept of equivalent stiffness because it will be very useful from now on. I have a skin with a whole bunch of stiffeners. The spacing between the stiffeners is ds, and the panel width is BP. So BP is the panel width. So the number of stiffeners is approximately the width divided by the spacing between the stiffeners. In fact, it will be exactly the integer that you would get if you divided BP by ds and rounded down. So if the answer is 3.7, it's 3 plus 1. So this is the exact number of stiffeners, if you will. Yes? Because if you do it, you will find that it doesn't work. Well, okay, I'll tell you why you round down. Because in computers, when you use this command, it always rounds down. So you can use the Kemal definition, which is perfectly fine with me, if you understand this as finding the integer rounded up from this division. If you can keep the two definitions from computer functions to and software, and the Kemal definition clear in your minds, then more power to you, because it's saving you adding +1. Fine. As far as I'm concerned, this is the exact version, but if I have enough stiffeners, lots of them, then the error by neglecting this one, or the error by, I am causing this. The error is very small. Now, when exactly you can make this approximation and get away with it, and when it actually introduces an error that you wouldn't want, it's up to you. I can tell you up front now, typically if you only have 2 stiffeners at the 2 ends, this is not a good approximation. But in general, with more than 4 stiffeners, you are fine. And that's, again, based on experience. It's not guaranteed to be good enough. So let's calculate, or start calculating, and we'll continue on Friday. What's the membrane stiffness, the EA, which you can represent as the A matrix, because A matrix is EA divided by width. So we showed way back, last lecture or the lecture before, that if I have a whole bunch of members under uniaxial loading, the EA of equivalent for all the members is the sum of the individual EAs. So by using that, I can write, if I take that equation and I divide it by width, I can write what's shown here, that the AI equivalent for the entire cross-section, skin and stiffeners, will be the AIJ of the skin, or the A matrix of the skin, plus the A matrix of the stiffeners. That's because if we said A matrix is EA per unit width, and that's EA per unit width. So, and the sum of the EAs, according to what we showed before, gives us the total equivalent EA. The A of a stiffener is the number of all the stiffeners, is the number of the stiffeners, NS, that we were talking about here, times the A corresponding A contribution for a single stiffener. And the A for a single stiffener is the EA of that stiffener divided by the width, basically, the full width. So EA of a single stiffener divided by the width of the panel gives us the smeared EA or A matrix contribution for a single stiffener, and multiplied by the number of stiffeners is the term I need to put in there. Now, because the NS, and I'll be finished in 30 seconds, NS is approximated as BP divided by DS, as we said before. And I multiply the NS here by the A for a single stiffener, which is EA, divided by BP again. So these will cancel, and I get what's at the top right as the contribution to the A matrix, A11 term for the skin and stiffeners, A1 of the skin plus this term, which is the EA divided by the spacing of the stiffeners. We will continue next Friday.